Queue management. See, various queue management types are there. Whichever suits your environment, you can choose one. Starting from priority queue, but the priority queue is not explained in this presentation because it is priority queue. You will have one queue with a fixed bandwidth, and you will map on certain traffic to that queue. Only for that traffic, that queue will be always kept uh, kept ready, blocking the bandwidth. Instead of saying blocking the bandwidth, reserving the bandwidth. That is priority queue. Priority queue is a queue which will be always there even when there is no traffic. Even when there is no that particular traffic which is supposed to take that queue. That is priority queue. I have not explained that in the presentation, but it is coming in some configurations inside. So what we are going to see is weighted fair queue. See, this priority queue is one selfish queue. Only that particular traffic can use the bandwidth. And if you have such, or if the priority queue consumes, let's say, all the bandwidth, other traffic cannot go. Assume, I'm just saying, you have 100 meg bandwidth, and you have given all 100 meg to the priority queue. Can any other traffic use the network? No, because you got only 100 meg. So they came up with another type called fair queue. Fair queue is like you create many queues and map different traffic to these queues, different traffic to different queues. You map it, and then first queue will be processed first while others are waiting, and then second queue while first queue and the others are waiting, and then the third queue while first and second queue and other queues are waiting. Likewise, it will go in round robin. That is fair queue. What is fair queue? You do some fairness in queuing. You allow all the queues to be sharing the bandwidth equally. That is the matter. Equally. Fair queue is you have multiple queues. Each queue has got different type of traffic to carry, to allow it to pass through. All gets a chance to use the bandwidth, but when one queue is active, the others are waiting. This waiting may not be good for time sensitive traffic. Here we see the fairness. See, I'm not talking about weighted fair queue. I have not gone into the topic. I'm just giving you the background. What was there before weighted fair queue? Before weighted fair queue is simply fair queue. Fair queue is you have multiple queues. Queue number 1, queue number 2, queue number 3, queue number 4. All have got equal bandwidth. When the first queue is using this hardware queue of the router, fast Ethernet 0/0, is the port hardware queue. First queue uses, while the other queues are waiting. And the second queue uses, while the other queues are waiting. Good news is everyone can use this. Everyone can use this interface, but not all at the same time. This is fair queue. What is priority queue? Priority queue is a queue which will always go and block certain amount of bandwidth in that hardware queue. Even when there is no traffic to go, this reservation will be always there. So there is only little bandwidth left for the other traffic. Which is not cost effective if you have more traffic, more types of traffic. That is why came that wait. That is why came the fair queue. We have seen PQ and FQ now. Fair queue. Fair queue is you have multiple queues with equal prioritization, with equal weightage, with equal importance. And when the first queue is using the available resource, the other queues have to wait. It comes in round robin, up to down and again down to up, goes in round robin fashion to consume the bandwidth that is available in the outgoing interface. It looks good. Which one is looking good? Fair queue is good. But not all traffics are same in prioritization. We don't give same importance to all traffic. Some are time sensitive traffic like voice, and then video, then multicast, UDP traffics. So what I'm trying to say here is the different important traffic should be given that importance, even in queuing. That is why comes weighted fair queue. You give the weightage. You don't give same weightage to all traffic. You give different weightage because you got different types of traffic. You give different weightage for the FQ that you learned already. Fair queue is equal weightage to all queues. Here, different weightage. To ensure that different type of traffic is handled fairly based on the predefined weights. You see, along with the fair queue, you attach weights so that you can give fair bandwidth allocation. More weightage, more importance. It's not equally given importance. It is according to the weightage. See, example, it is designed to provide a fair bandwidth allocation to different flows, not same bandwidth allocation. See, Some traffics need very less bandwidth, where some are bandwidth, what to say, hunger, bandwidth hunger traffic, like file transfer protocol uses huge amount of bandwidth hunger traffic, whereas voice traffics are tiny traffics, very small packets. Voice traffics are UDP traffics, not much encapsulation, not much payload. So what you can do is you can give less bandwidth to voice, but more priority. Usually we don't give voice the WFQ. We don't put voice in WFQ. We put voice in PQ, priority queue. And we don't give too much bandwidth for the voice because voice are tiny packets. So in the real world, what we do is, if this is your router and this is the interface, outgoing interface, we put one PQ here. That will be always waiting only for voice to use. So inside you are configuring this software queue, and this is PQ. And below, you put many WFQs. So anything enters into this PQ will only take this. And these one, according to the weightage, it will be decided who will go and use this bandwidth and how long, how much bandwidth of this traffic should go out. After that much bandwidth goes out, then how much bandwidth of this next queue can use this. And then once that limit is reached, the bandwidth given for this queue member, this queue traffic will be given, and then again goes in round robin. Round robin only for WFQ. This PQ will be always there. So weighted fair queue is a type of scheduling algorithm used in networking specifically to manage traffic in network routers and ensure different type of traffics like voice, video, data are handled fairly based on the predefined weights. It is designed to provide fair bandwidth allocation to different flows of traffic while prioritizing more important or time-sensitive flows. Any question on this? Now, weighted fair queue key features. Fairness is nothing but weightage. According to the importance, fairness is nothing but importance. We set weight. Weighted fair queue assigns a weight to each flow. A flow refers to the continuous stream of data between source and destination. Everything is explained here. I'm just reading. Weighted fair queue assigns weight to each flow. I told you not all flows are of same importance for users. So according to the importance of the traffic flow, what is a flow? It is the continuous stream of data between one source and destination. I don't want to put my own words. These words are very excellent words. It conveys the real depth meaning of what I want to say. A flow refers to the continuous stream of data between source and destination. So for each flow, a weight is assigned. The weight determines how much bandwidth this particular flow to be given. Flow with a higher weightage is given a more bandwidth. Higher weight, more bandwidth. Lower weight receives less bandwidth. And fairness is ensured by giving each flow a share of available bandwidth, based on its weight. So they're going to share the bandwidth. The one with a higher weightage may be going and using the physical hardware queue long time because they're given more bandwidth. That much amount of data should go out. Traffic coming out from the less weight queue will use the hardware queue just less time because less bandwidth traffic only allowed for that queue. Understand? I want to draw again and explain. No. Yeah, that is no. Both are available depending on the queue type. For this weighted fair queue, it will be automatically allocated. Okay, for your question, yes, automatic. Provide the weight. Yeah. Now this red one is a PQ. That PQ has got already the reservation. Inside this, it will go non-stop. Non-stop. PQ is non-stop. This PQ traffic will never be interrupted. Anything that enters into that red tunnel, these are all software queues. This is the queue that you create. But this is a hardware, physical one. Now, other than PQ, now we are talking about weight. You see, according to the weightage, see the size. This has got more weightage, that's why bigger pipe. It's more bulky, no, compared to this one. Let's say this consumes 10 liter. This consumes 5 liter. This consumes 3 liter. 3 liter tunnel, 5 liter tunnel, 10 liter tunnel. So now 10 liters of, let's say, water, 5 liters of milk, and 3 liter of oil. We have these three. Now, when water comes, this entire remaining bandwidth will be given for water till this 10 liter goes out. And then comes the 5 liter milk. The complete 5 liter, only 5 liter again, it's not 10 liter. Only the 5 liter can go and consume, all the remaining bandwidth go out. So the time taken by water and time taken by milk will not be same. According to the weightage, it varies, you see. More weightage, more bandwidth is given, meaning what? 10 liters can go out. More bandwidth is given, more weightage. 10 liter can go out. Less weightage, less bandwidth. See, the bandwidth here is not varying, but the amount of traffic that goes out is more bandwidth. When oil comes, only 3 liters is allowed to go out, and then again goes to water, finish water, and then comes milk, finish milk, and then only comes again oil. You understand this?
Yes, sir. Sir,
Hmm. Hmm. You see, listen, whatever the QoS that you configure will be effective only when congestion happens. Otherwise, they will all go parallelly at the same time. All right. See, that is why it is called as management. Congestion management method is queuing. Queue management is congestion management avoidance. Congestion management. Queue management is congestion to avoid a congestion occurring more. Now, fairness is ensured by giving each flow a share of available bandwidth based on the weight. Packet scheduling. Weighted fair queue is a packet scheduling algorithm. We just explained the packet scheduling. What is the type of packet that is scheduled for this much amount of bandwidth? Accordingly, the time will be taken. Milk, again, it is scheduled for this much amount of bandwidth. Accordingly, time will vary. That is how oil, everything varies. So WFQ does this. WFQ is a packet scheduling algorithm. It organizes the transmission of packet from different flows in a way that each flow gets its fair share. The share is not equal. The share is according to the weightage. So they have their own fair share to consume the network resource. It uses virtual time. For a 10 liter, how much time it takes? For a 5 liter, how much time it takes? For 3 liter, how much time it takes? They're not same. And again, these are all virtual times. We don't fix it. According to the bandwidth, it will schedule. Okay, for 10 liter, for 10 megabits, this is the time for this queue. For 5 megabits, this is the time for this traffic to use the queue. For 3 megabits, this is the amount of time it can use the resource, the hardware queue, the resource. So it is the WFQ taking care of all this timekeeping thing. It uses virtual time to keep track of when each packet would have been transmitted if there were no other flows, ensuring no flow is starved. This is the main point. Why do we have this fair queue? Others no need to wait. Everyone should get chance. And everyone should get chance is fair queue. Everyone should get chance, and it should be as per the weight. That is WFQ. Everyone is getting chances, simply fair queue. Everyone gets chance, but some get some additional service compared to others. That is WFQ. Like as I said, water gets more, though all three are getting chance, water, milk, and oil, all three are not getting that same service. It is depending on the weight. That is why it is WFQ, not simply FQ. Simply FQ is equal amount of virtual time. Equal amount of virtual time is FQ. This is not equal amount of virtual time. Virtual time will be different for different Q with different weightage. Okay, queue management. WFQ works by maintaining a queue for each flow and scheduling the transmission of packet from this queues in a way that reflects their weightage. So how much weightage? According to that, the transmission of packet, the flow, the amount of packet is determined. When packet arrives, they are assigned with virtual finish time. This is what? See, the flow weightage is what going to decide the finish time. Very nicely explained. Water finish time and milk finish time and oil fish finish time are the same? No. Depending on the weight 3, 5, and 4, 3, 5, and 10, the finish time is going to be different. The virtual time that will be calculated and assigned will be different. When packet arrives, they are assigned a virtual finish time based on the flow's weight. The packet with the lowest finish time is transmitted next. This is another beautiful thing. Now, which one will be finished first? Is it 10 or 5 or 3? See, amount of bandwidth given to water is more compared to milk and oil. But the problem is the virtual time will be more for that. So instead of making this tiny oil till that bandwidth, hunger, water consuming the resource, you do the reverse. See the small one. First allow that one, finish it. Because the wait time will be less for milk and water. If water goes, milk and oil need to wait long time. Because water is going to go for a long time. See, bandwidth is given more according to weightage, but who goes out first? The one with the less virtual time. Who has got less virtual time? The one has got less weightage. Bandwidth is also given less. So time taken will be less. Because the time taken will be less, allow that to go out first. It won't take much time like water. So finish oil first and then milk and then water. See, when the packet arrives, they are assigned with virtual finish time based on the flow's weight. In the previous paragraph, we saw big weight, more bandwidth. Now you are seeing the packet with lowest finish time is transmitted first. 3 will be first and then 5 and then 10. Weighted fair queue advantage is what you have different type of flows. Not all flow needs same finish time and bandwidth. So accordingly, you do the weight configuration so that mixed traffics can be handled effectively. So WFQ is used in an environment where multiple type of traffics like voice, video, data are being transmitted over the same network link. Weighted fair queue ensures that the time-sensitive traffic like voice is given priority while still maintaining the fairness for less time-sensitive traffic. Means all are given attention. All type of traffic are given attention. Optimal of real-time traffic. Weighted fair queue is well suited for real-time applications like voice over IP, video conferencing, as it ensures minimal delay for high priority flow, while still providing the same level of service to the low priority traffic. Now you see, here they are using voice repeatedly, but we are under the topic called weighted fair queue, so they are taking voice as an example. But in the real world, we don't really use WFQ for voice. As I said earlier, you have PQ. Because voice never tolerate delay. Between source and destination, there cannot be more than 300 millisecond delay for voice. Voice cannot tolerate that. More than 300 delay between source and destination. I'm not talking on one router. Between source and destination, voice cannot tolerate more than 300 millisecond. So we don't really put it in this wait fair and all. Wait a fair queue, wait a fair queue. We don't really do that. We put it in PQ. PQ will be never delayed. Whenever a data comes in, PQ will be immediately pushed out. No round robin, no waiting, nothing. But here they are using repeatedly voice. You should understand that we are not doing overall QoS summarization. We are learning one type of queuing management called weighted fair queue. So you should not get misguided thinking that voice will also wait for some time when others are being fairly served. Not really. Just here, for example, they want to say that's very important traffic. We the real-time application traffic. We ensure that there is a minimal delay. See, minimal delay for the high priority flows, while still the provisioning some other with low priority. Means all are getting served, but for the high priority, we want to make sure that there is no much delay, minimal delay. But definitely compared to PQ, there will be more delay in this WFQ. That's why we don't put voice in WFQ, we put it in PQ, which will come later with another topic called LLQ. Consolidation of all this you are learning, WFQ, PQ, will come later in one topic called LLQ. But before that, we need to first of all understand the configuration side of this WFQ and then few other queuing methods. Then we will go to that final one. So far, you have learned three queuing methods. Two are not mentioned. Number one is PQ. Then the second one is FQ. The better version of FQ is WFQ. So you don't need to worry about FQ. Configuration of FQ is very simple. Just put fair queue, that's all, under the policy map. I'll show you. That's why I did not include in the presentation. When you know WFQ, FQ is without wait, that's all. Next, how WFQ works. WFQ maintains a virtual finish time for each packet. When a packet is arrived, it calculates the finish time based on the flow weight and the current state of the network. The packet with the small finish time gets transmitted first. This approach gives high priority to the flow with a higher weight. Okay, sorry. Uh, I compared this with bandwidth, so it went wrong in the previous slide. What I'm trying to say is the the small finish time gets transmitted next means it is not transmitted now. What is transmitted now is the one with a high weightage. Finish time is based on the flow weight. The packet with the small finish time gets transmitted next, which means the packet with the higher priority, with higher weightage, with high finish time is served first. Correct. That's the drawback of this. That is why we'll be moving on to class-based weighted FAQ, which is coming next. I mixed both. All right. So here, high weightage, high priority, high finish time served first. Small finish time is served next. So what is the problem in that? Water will be served first. Water will be served first. That's the drawback of WFQ because it has got high weightage, high virtual finish time. The small virtual finish time served next, which means milk is next after water. So when the huge water goes out, the milk and oil will wait long time. And then when the milk is going, oil and water should wait. So there is a drawback you see when the traffic with a high virtual finish time is using the bandwidth, others need to wait a long time. Instead, if oil is sent first to the small one, and then milk, and then water, it will be fine. That is coming next method. That is not WFQ. That is class-based weighted FAQ. In between, in front of W, you put C, B, class-based weighted FAQ. It is coming next. So, arrival of packet. When a packet from different flow arrives, they are assigned a virtual finish time based on the weight, flow weight, and the state of the system. Packet with a small finish time or trans. Oh, come on, they are confusing me now. I don't know why they use the word next here, so I changed my version. Now they are again going back to my older version. The packet with a small finish time are transmitted first to ensure the high weightage flow gets more bandwidth. Okay. Again, they come back to my old story. Anyway, this is the principle. This is how it works. Okay. Try to manage with this, and you have your own understanding now. Here, what they are saying, they are going back to our old story. This will be given first preference. Oil will be given first preference. Milk will be given next preference, so that water will go peacefully because there is no one else to consume the bandwidth. Something like that. That is what I was telling me in the beginning. But this one transmitted next confused me. So you be a judge. The packet with the small finish times are transmitted first. This ensures that the high weightage flow will get enough bandwidth. So this is only focusing on the bandwidth. This focus mainly on bandwidth, not the time. This method want to make sure the one who needs more bandwidth gets that bandwidth. For that, you finish all the small guys, you will have enough bandwidth. Say, for example, when there is a traffic jam, don't try to send the big lorry first. Send all these bike guys, the people in bike, that small auto, clear them first, then it will be easy for the big lorry to go freely. Exactly the same scheduling approach is there in weighted fair queue, right? So that the one who needs more bandwidth will be having that bandwidth when you finish sending all these scooters and autos and small auto car first, instead of sending that big bus or a lorry. Fairness and priority. While each flows get a share of bandwidth based on its weight, real-time traffic is prioritized to ensure low latency. Yes, that is the main aim. You don't want more latency. Advantage. Fairness. It ensures fair bandwidth allocation based on weight assigned to each flow. That is the meaning of fairness. Flexibility. It allows for prioritizing certain flows like voice, video, which requires low latency and higher bandwidth. Prevention of starvation. No flow is complete, starved of resource. Everyone gets the privilege. No one is starving. Even one with a lower weight gets served. Okay, disadvantage. Complexity. Weighted FAQ can be competently expensive and more complex to implement compared to the simpler queuing method called first in first out. See, first in first out is not at all real QoS. Whoever comes first, they will be using the resource first. For that, there is no configuration, there is no algorithm, there is no additional CPU, so there is no complexity. Here, definitely, you are doing something. You are creating queues for each flow, which is going to take some additional load on the CPU. Algorithms are used, so additional load on the CPU. Actually, you cannot call this as complexity. This is necessity, isn't it? Signal lights are necessity. Putting signal lights will take some money. There is no doubt. If there is no signal, you don't have that expense. But managing traffic is not easy. First in, first out is not easy. Even when something important traffic come, they will be waiting at the back. Ambulance. Because there is no signaling, there is no proper system in place. So you cannot call it as a disadvantage. That expense is disadvantage or complexity. But compared to FIFO, this is going to take some CPU because there are algorithms involved. There is going to be a manager which maintains the virtual finish times for each queues, which is also going to increase the CPU utilization. Scenario. You have a router interface where you want to apply WFQ to prioritize voice traffic while ensuring the other traffics like HTTP and FTP also gets fair access to bandwidth. You understand? This is what we are going to see as an example configuration. This demo and I am not going to do because the commands that I'm going to show will be very clear. All that you need to do is you need to type those commands, and then I'll also show you the verification command. You need to verify, that's all. Because everything is there in the presentation, I'm not going to do this demo, you will do it. So what is that example configuration that I'm going to do? It is going to provide voice a very good priority. At the same time, it also gives importance to the other traffics like HTTP and FTP. so that all will get served when there is a congestion. No one is going to starve for any reason. Okay, first step is you need to define a class map in which you are going to identify the voice and the other traffics like HTTP, FTP, etc. Class map match any is optional. You don't need to say match any. The default is match any. Class map voice traffic. Voice hyphen traffic is the name given by you. You are giving this name. This is optional. Even if you don't give, this is what will be applied. Class map voice traffic. Match IP DHCP EF. You know this one. I already demoed this. How to attach EF to voice traffic. In the other router or a switch, you write an access list to match all the voice traffic, call the access list in the class map, and call the class map in the policy map and say set DSCP EF. And then you go to the interface and say service policy map and call the policy map outside. This is explained in the demo earlier. Now, packet is coming from that router to this router with EF already marked. You are matching that one here. This is on the second router. First router is marking EF for all traffic and sending to you. On the second router, you are matching those EF marked traffic in this class map. Did you get that? Did you get this point? What I just explained, EF. Already got? Very correct. So that EF you are matching here. And for data traffic, like HTTP, what you do here, you create another class map called data traffic. This is user given name. You give any name. Coupon traffic, Kansame traffic, that's up to you. Some meaningful name, voice, data. No, that is good. Now, here you are saying match IP DSCP default, meaning you are not going to give any special priority for other traffic. You are just saying first in, first out. That is default. Default means best effort. Now, whatever is already marked, if it is marked already, other traffics like AF11, something like that, AF32, that is going to be taken, considered. Now, second step is, after finishing policy class map, the second step is policy map. This is the place where we are going to allocate bandwidth using WFQ. So we are saying policy map, any name, WFQ policy is one name, it can be any name, coupon policy, no problem. And call the class that you created earlier. Earlier you created voice traffic, this one. Where you are calling here? Voice traffic. And then you are setting 1000 kilobits of bandwidth by putting this command, priority 1000. Right? So here you are saying priority 1000 creates the PQ. Understand? This is creating what? A PQ for you. You are not using bandwidth command, you are using priority command. That is why I did not teach that as a separate topic. When you use the keyword priority 1000, it is a fixed queue for voice. That queue will not be tear down. It's permanent. And for the rest of the traffic, you remember we created another class there on the previous page. There, for that, you are setting 5000 kilobits. All right. At last, you go under the interface and say when the traffic is about to go out, this is how the treatment needs to be given. Do according to what the policy map called WFQ policy tells you. What does it tell? If the packets are EF marked, then 1000 kilobit queue it should go. And that queue is a permanent queue, priority queue. For the other 5000 kilobits queue is there, you can place them there. So totally here two queues. One is PQ, another one is the queue, which is shared for multiple flows. To verify, this is the only command you need. Show policy map interface geek01. It will show you how the traffics are put it into queues and how many packets have been sent and received and how many got dropped. For painting the wall. 1,500. Got it? So, summary, class map you created, you match the EF. Papa, for other traffic. 3,000 you have to give us. You did best effort, and then you went into the policy map. You gave voice traffic 1000 kilobits priority queue. For the data traffic, reservation of, not reservation, bandwidth is given up to 5000 kilobits. And then we went under the interface and say outbound. When the traffic goes, refer this policy map. To verify, we say show interface policy map, show policy map interface. All right, so we have really finished one very big topic called WFQ, which includes PQ and FQ. All right, we have finished this one big chapter called WFQ. Next is class-based WFQ. Class-based WFQ is you're going to have more number of queues. In the early scenario, you saw only PQ and then one more queue of 5000 for rest of the traffics. Not much. But here you're going to create various classes. Along with PQ, we can have various classes. See this example, you see? Class A, weight 3. Class B, weight 3, weight 5. Class A is weight 5. Class C is weight 2. You got multiple weights, different levels of bandwidth for each class, and they are going to be placed inside the queue later. So you can see here, for voice, EF, that's one class. For video, some DSP, maybe AF41. For the rest of the traffic, see this piece was not there in the WFQ. Creating more classes. That is why this is called as class-based weighted fair queue. At last, you call all the classes. For each class, you see, one will be priority queue, the other will be bandwidth. And then you apply, as usual, on the interface outbound. All right, that's the difference. I want you to go through this one yourself. All right, class-based weighted fair queue. It's similar. Only thing is you can have more number of classes, not just one PQ on another class. You can have more classes. And for each class, you can have different priority. More granular control. That is the beauty of this. And the configuration example is very clearly given here. Right, this is the scenario. Why is 40% of bandwidth? Means 40 meg out of 100 meg you should give. For video, 30 meg. For other general traffics, 30 meg. So totally 60 meg is properly utilized. Apply that on this. All right. So for that, steps are explained here. You see class map, match EF traffics, and then another class map, match all the RTP traffic, real-time traffics, protocol. You're matching the same protocol, not DSCP value in this example. You can also match DSCP value like what you saw here, AF41. Here you can, they are showing another match, like you can even match protocol. And for all the other protocols, FIFO, that's called general data. Right, now, under the policy map, you call the class first class and give 40% of the bandwidth, priority 40, and you use the keyword priority so that it will be a priority queue. And then class video, you give bandwidth 30, bandwidth 30. These are all flexible queues. It will be used and then broken, used and then broken. But this queue will be permanent. That is why the word priority. You can use only once the priority. All right, so explanation is given. See the guaranteed 40 meg voice gets via the priority queue. Right, what is low latency? So we have covered even class-based weighted fat queue with configuration. The final one is low latency queuing. Low latency queuing is nothing but priority queuing and the class-based weighted fair queue. Both together is low latency. So this is not new. This is known to you again. The early one and the very beginning one. Very beginning one is priority queue. The early one which we just finished is CBWF queue. Put together, you will get low latency queuing. Why do we do this? So that the voice will be always going in the priority queue, which will never be considered whether to drop or slow down when the congestion happens. Only slowing down or dropping all those decisions happens only for those that are in CBWF queue. PQ will never be disturbed. Let's see one example here. You see, you're matching EF traffic here for all other, you've set default. So here we are seeing EF, which is going to be placed in PQ, and the other traffics are going to be in CBWF queue. This example is not that detailed, but okay. But the previous examples for CBWF queue were wonderful. So here, this is the example. Voice traffic is given priority and guaranteed of 1000 kilobits. Data traffic can use any remaining bandwidth up to 3000 kilobits. Let's see how to do this. And then assign it to this interface. Sorry, that example is not. Okay, this is what they are. Oh, here it is. Sorry, this is a policy map. So this class, which is already created as voice, is given. It's not properly arranged. That's why I got confused. They should come in the next line. Is given priority queue of 1000, whereas the other class called data is given 3000. That's it. So this word priority is what makes difference between WF queue. But in the real world, we always use the priority queue for voice. That's why even in the previous example, it was there. But it's supposed to be only in the low latency queuing topic, LLQ. LLQ is the combination of this PQ and class-based weighted file. This is what we use in the real world. What do you see? This one. The best is this. The best LLQ example they have put under here. 3 different classes. 1, 2, 3. There'll be more also in the real world, like 20, 30 classes. This is actually LLQ. LLQ is nothing but, along with the PQ, you use CBWFQ, right? That's all. So the entire QoS is covered for you, maybe 4 or 5 videos. If you watch these videos, you will be considered as a master of QoS. Once you try doing the lab, only one output command, show policy map, the interface name. It will show you how many packets went through PQ, how many packets went through CBWFQ, how much packet got dropped because of excess package, so on. Any question?